Unrecognizable. That's what you are, as the old song goes. So we want to speak about those languages that are above Turing machine decidable, which are recognizable. So a language is decidable, Turing machine decidable, if and only if there is a program that always stops and accepts the language, right? And a language is recognizable if there is a program or a Turing machine that, if the word is in the language, you feed the word into this Turing machine, it runs on it and it accepts. If it's not in the language, you have no guarantee. And the Halting theorem was just that ATM, this language of machines and strings, such that M accepts W, this language is not Turing machine decidable, but we showed that it in fact recognizable. Okay, so we have at least one language which is recognizable but not decidable. But here is a very cute lemma that shows that if I have a language that is recognizable and so is its complement, then they are both decidable, or at least one of them is decidable. The important thing, by the way, is that if a language is decidable, its complement is also decidable, because for a decidable language, the Turing machine or the program for this language always stops. So, if it returns true or false or reject accept, you can always flip it. So decidability is closed under complement. So the claim here is that if both languages complement are, as I said, recognizable, then they are both decidable. Okay, now one has to be a bit careful here, because what does it mean, a complement language, right? So a complement language naively is just all the strings that are sigma star minus the language, but that contains a lot of strings that we don't care about, right? If you think about ATM, which was all the strings that M stops on W on, the complement language is not all strings except this. It's really the interesting complement language is all the string M, such that W does not stop, M does not accept W in this case, right? So the way to think about it is that when we do the complement, we're going to be a bit not careful, right? We're going to use the complement notation, but usually when we say complement language, we really means all the complement, all the string in the complement language which comply with the formatting and are valid input for the original language. Okay, this is a side comment. Okay, so how do we prove it? The proof is very easy. We build two machines. Let's assume that M recognizes L and MC recognizes the complement language. So we have two Turing machines, and then we feed both of them the input, and we do it in parallel. We run both machines in parallel. Now, either the word is in the language or it's not. So one of those machines, either the machine for L or the machine to the complement, must stop. If it stops for L, then we accept. If it stops for stop and accept for the complement, we say it's in the complement, and this is it. We are done, right? So why? Because all we are using is the fact that the original machine or the complement machine would not stop, but one of them must stop. As such as we run them in parallel, we will stop as soon as one of them that must stop would stop. So the problem becomes decidable. But that, this is what I just said about the complement language. But that implies readily that the complement of ATM is not Turing machine recognizable, because we know that ATM is Turing machine recognizable, and by the lemma we just claimed is that if this was recognizable, then ATM would be decidable. But we know that ATM is not decidable, so it must be that this language is not recognizable. Right? So we are done. Okay, so this is now very weird. So by the way, it's kind of useful to look on this complement language, ATM, complement ATM. This is all the pairs M and W such that M does not accept W, right? So somehow the fact that M does not accept W, deciding this is harder than deciding if M accepts W, because M does not accept W include the fact that M might run forever on W. So this is a harder problem, which is weird, but this whole lecture was full with weird things. This is it.